Here it is. Where it is. Okay. So today we have the pleasure to hear from Víctor Jaramillo about complex structures of boson star and anisotropic distribution of satellite galaxies. So Víctor is a postdoc in the University of Science and Technology of China. So please, Víctor, the floor is yours.
Thank you, Jordan, for the introduction and also for setting the presentation. I will present some dynamical solutions of boson stars which are motivated by some founded solutions in the flat space non-topological solitons. This is basically this kind of solutions are reported in a paper that I worked with my boss, which is Jaramillo, and we are in different places. I'm from the astronomy department, and he's in very close in this center of fundamental physics. So he works in some QUBO kind of stuff. And he told me about this charge swapping kind of solutions that people know that exist in flat space. We managed to include gravity to see what happens with boson stars. So the original title is complex multipolar boson stars, but actually a more concrete title would be like this one: charge swapping multipolar boson stars, because it is possible to obtain configurations with different morphologies. I will first motivate these kind of solutions. Then I will say what I will include gravity to show that it is possible to obtain these solutions. This second part, it is just a small modification from the QUBO cases, which include a potential, which is not a free field potential, of course. And after this, I will discuss the full details and discuss what gravity does in these kind of configurations when we turn off these self-interacting potentials, focusing on the free scalar field case, which is more transparent and more easy to analyze. And after all of this, I will give one application of this kind of configurations, which is a cosmological application regarding the anisotropy of satellite galaxies in the Milky Way. So first part, what is a charge swapping QUBO? And before saying this, I need to say what is a QUBO. Many of you, I'm sure you know, but in any case, I will say here, it is just a soliton regular-like non-topological solution of this kind of theories, which is a complex scalar field with a potential. And for example, in spherical symmetry, you can put these ansatz. The metric is just the Minkowski metric, and then solve the Klein-Gordon equation, and you take these kind of solutions for the radial profile of the scalar field. These solutions, in particular, are solutions of this theory here, which is a sextic potential. And what is a charge swapping QUBO then? So these solutions are, they appear when you make a superposition of two QUBOs. So if you place initially two QUBOs very close to each other, let's say you have a QUBO solution, a spherical QUBO solution, and you take a second QUBO solution, and you let some of the configuration to superpose. Then, because of the non-linearities of the field, this configuration will undergo some relaxation process. And after this, the attraction of the two components, which is not trivial to explain, but you can show that it happens, that some attraction of these two components, the system is bounded. So this configuration starts to swap charges. These are said to be a positive netter charge, and this one is said to be a negative nether charge, which is basically controlled by the frequency omega of the solution of the initial ansatz for the scalar field. And then these charges will start to exchange, and it will behave more or less stable during a long period of time or a very long period of time, depending on the specific potential that they choose. And this is what a charge swapping cubewall is. Yes.
So you have two fields, right? Not single field configuration.
Yeah, it is a single field. So you have a total potential, which is a sum of two fields, phi 1 plus phi 2. Let's say phi 1 plus phi plus phi minus. This is I to the phi omega t, and this is minus I to the omega t. And they are placed a little bit far apart, not too much, because if you place them very far apart, they will repel or they will do whatever they want. You have to make sure that they are superposed at t equal to 0. And usually, if they have tested that in every theory that they can think about with a potential V, they also exist these kind of solutions with very different properties according to the potential they use. These are no longer stationary objects. They have never found any kind of, temporal decomposition of this field such that you can calculate the whole evolution of this system. What they do is that they make this superposition and they let them evolve using numerical codes.
Form these objects dynamically. I mean, you have two other stuff and you just, you will repeat that these objects is that my question.
Yes, for example,
When you form these objects dynamically.
I will show that in boson stars it's very natural to think about the generation mechanism of this kind of configuration. In boson stars, it is basically the collision, the Henon collision of this of two boson stars with different charges. In the context of cuballs, it is I don't know precisely. And let me say also that these configurations constitute a tower of solutions. And this is because not only the dipolar configuration can be formed, but also multipolar. So if you're in 3 dimensions, you can build a quadrupole, octupole, and so on. And the same process happens if you superpose more cuballs. When the cuball is formed, this kind of evolution happens. This is just what I was drawing in the whiteboard, which is the process of charge swapping. It begins with certain total value of the charge on the top and certain negative value of the charge on top, and it will exchange during time. This is very well within the charge swapping period, which I will detail more how precisely these are formed later. The previous plot was just the nether charge density. Okay, that's why you see a positive and a negative values. But in this plot, I am showing the energy density. So these configurations are spherical, are almost spherical, but they are dynamical configurations. There is actually a small deformation. These are not perfectly spherical solutions. And this is the reason we thought about this cosmological application about anisotropy in the halos, in the dark matter halos. This comes also from discussions that I had, that we had in my PhD with my advisor and other professors in Mexico, which work a lot in this kind of halos of dark matter. Well, this is the original paper where they present the charge swapping cuballs. This is my boss, and so he told me to couple this to gravity, and this is what I did. And to do this in a minimal way, the first thing to do is, of course, take the same potential as the cuball case and include gravity, and couple minimally the scalar field to gravity. You have also to solve for the metric function in these cases. So we explored actually three kinds of potential, but first I will focus on this one, which is the same as the QBO. And let me say that this is the logarithmic potential, which is the one that they used originally in the first paper about charge swapping solutions. And this potential, it is of course a limit of this potential when you take lambda equal to 0, but I will show that it is very easily recovered by taking some limit regarding the effective gravitational potential of the solution. We do this change of variables, which absorb the dimensions of the system. Now everything is dimensionless. And by doing this, we obtain an effective gravitational constant, which is inversely proportional to lambda. And this effective gravitational potential, which is the only free parameter together with calligraphic G, appears in the Einstein equations in this way after you do the rescaling. Let me say also that we will focus only on the case where calligraphic G is equal to 0.5, and it is possible to see by the Einstein equation that this limit is the Minkowski limit, and this limit, which is alpha goes to infinity, it is the free field case. And you can convince yourself by looking at these definitions of the dimensionless variables. So we will not study this in separate, but just take a limit of this case. And in this way, we will arrive to this Einstein-Klein-Gordon system, and we will need to solve this Einstein-Klein-Gordon system in three different parts. These are not steps, but these are three different contexts in which we need to solve this. First, of course, it is to solve the solitonic spherically symmetric solution. This is done by plugging some ansatz in both of the equations and then solving this numerically and obtain the corresponding boson star solutions. They are also known as Q star in some contexts because it is a polynomial potential. I think some people call this Q star, but I'm not sure if this is a convention. After this, we need to make the superposition like this, but one difference is that since we have gravity, we need to solve for the constraint equation. And since we are placing both of the stars initially in equilibrium, that is in a time-side symmetric instant, then we will only need to solve the Hamiltonian constraint, not the momentum constraint.
Another thing, when you're doing the superposition of those two stars, how do you determine the overlap? Is that the overlap really matter, or you just have, for example, put the star that they just touch, or they have to have some specific range?
So we parameterize this by a distance d, and then explored many cases of d. We found, for example, that with this polynomial potential, if you take them very far apart, then they will repel each other. And this is important. This parameter is like you have to be careful in the case of a sextic potential. You have to put them very close initially. But for the other cases, it is the opposite. You have to place them far apart so that when they collide, they expel some energy, and after this, you can form this kind of configurations. It is important to make several cases for this parameter t. So first, and to solve this three-part problem, so it is ideal to use the 3+1 formalism. It is well suited for this. For the first part, we construct the static spherically symmetric configurations, which are configurations like this. This is more or less known in the literature, maybe not with these particular values of the constants of the model, but basically these configurations have, this is very close to the mini boson star case, which has one stable branch here, and then all of these configurations are unstable. But when you start to include this kind of self-interactions, you find that you have two branches of solutions, of stable solutions, one which is here and the other one is Newtonian branches of solutions here. One interesting thing about these configurations is that you can reach high compactnesses and also some interesting properties like geodesic motion particularities of these kind of solutions. Just to talk about the scales of the system, if you choose this value of the mass of the scale of the boson, then you can obtain solutions that are of the size of kilometers and masses around the solar masses, for example. If you choose masses that are smaller, then you can obtain things that look more like halos, of the size of halos and also of the mass of halos. Notice that it is always possible in any value of, with any value of the mass of the boson to go to the left of this plot and obtain very dilute configurations. In particular, cosmological applications work in cases where mu is very small, and you go to the left of this plot, very big radius and very small masses. Well, I mean, very small masses compared with the radius of the system. Then I will explain how we do the preparation of these kind of solutions. So as I was saying, we just need to solve the Hamiltonian constraint, which simplifies to this equation here. Since we are interested in constructing not only dipolar but also multipolar kind of solutions, we need to solve this in 3 dimensions. And to do this, let me say just that this is the dipolar the dipolar superposition of stars, which is just what I wrote here. But what we do to solve this system in 3 dimensions is solve using Kadar. This is the way it looks, this partial differential equation. And actually, this system works and converges fine. But when we include very high compactness solution, it fails. So we are restricting to medium compactness kind of solutions or dilute solutions. After this, we evolve the system, and to do this, we just use some thorns that take these solutions from the spectral space to the physical space and take them to the Einstein toolkit to make those evolutions. We prepare these thorns that do the interpolation and also some analysis thorns to measure, for example, the nether charge and other things. This is the result in the case where there is, okay, so this is when you have the polynomial potential. And we did first the Minkowski test, which is just recover what people have obtained in flat space. And then we increase the value of alpha to this small value of alpha 0.01. And this is the value where we start to look some differences with respect to the flat space case. This is the energy. Okay, this is the energy of the system. This is time. And this is 2 pi T0, it is just equal to 2 times pi. And the difference we see with respect to the Minkowski case is that there is one more phase, which is the one here. Usually, in the Minkowski case, it relaxes initially. It gets to this plateau here, which is the charge swapping phase. And then it undergoes this fast decay, which is an exponential decay, and it goes to an oscillon plateau. In the case of gravity, instead of a final oscillon, you have an oscillaton at the end. And you have this extra step. And I think it is also possible to obtain extra steps. So it is a cascade of, it starts undergoing this kind of cascade of energy. And in the left plot, in the right plot, you can see the charge on the top part of in the up hemisphere. And you can see that it actually ends up with 0 total nether charge in the oscillaton phase. Yes.
Where does the energy go to, gravitational waves?
No, well, some part of the energy, some part of the energy go together with the scalar field. There is a scalar radiation, and there is also gravitational waves, I think. We didn't measure the gravitational wave, but I'm sure that, for example, this process is violent, so there should be some gravitational waves.
Do you have a comparison between this D and this R99 between?
Between D and
Well,
R99.
well, you
Oh, yeah.
have this,
Well, I don't have a plot or any equations, but yeah, it is something like D has to be smaller than R than 2 times R99.
so you're forcing them to.
Yes, yes. If I will have some tables in the paper, but I didn't put them here to show that actually D is smaller than 2 times R99. No, actually, I have this is the table. Um, no, sorry. I don't have any information about the D I used.
In the previous slide, you had like a label.
Right. Yeah, this is different values of D, which is 12, 14, and 16. And this is the configuration with alpha equal to 0.01. Okay, so you have to place them close, but it allows you to. Yes, and after this, we made a systematic study of this kind of solutions, which means increasing the value of the gravitational coupling. We find that some of the solutions actually collapse to a black hole as expected. And there's not much to say about these solutions, only precisely the question that they were making, that is that this kind of events should produce some gravitational waves that can be interesting to study. This is some application for these polynomial potential solutions.
Another thing, that C over there is the compaction, right?
Yes.
How do you find the compaction of these two, of this system? I mean, if you have that, how do you find the compactness? Sorry.
Yeah, I'm sorry. This is the table of the initial isolated configurations. Yes, I'm sorry. Yeah, so this is let's say the necessary things that you need to know before obtaining this kind of configurations. But what I can say about the compactness of these final configurations is that some part of the scalar field goes, and also they they become a little bit smaller in the evolutions according to the plots of the energy density. So the compactness of the final configuration shifts of the same value as the initial configuration, more or less.
And so when you superpose the two cuboids, are these the same but just with opposite charges, or can you also vary like they could not be equal mass or this kind of things?
Yeah, so they have tried to put a different charge but a different phase. For example, include some number here. And then they see that if they modify the phase, the results are the same qualitatively. And they have also tried, I have not tried, but in flat spacetime, they have tried to put not exactly the opposite charge, but something that it is opposite in sign, but different in magnitude. And this kind of configurations also form. They're not, yeah, they're relatively, how to say, robust in the sense that they can be formed with generic, more or less generic initial data. Yeah, so what I'm going to talk next is what do gravity do precisely in this kind of configurations. And to know this, we can restrict to the free field case where everything is more clear. What's the role of gravity? we explored these initial isolated boson star models. As you see, there are frequencies that are very close to the Newtonian limit. The Newtonian limit is over here. This is the frequency. Okay, it's frequency and mass here. And these four configurations are able to form a charge swapping boson star solution. These are, of course, very low compactness solutions. And here I say I am stating what is the minimum value of this distance d, such that the configuration form. So this is opposite to the case of the self-interaction case, because you need to put them far apart in order to be able to form. And this is just because these kind of configurations, you start to superposing two boson stars that are close to the maximum mass, and these solutions will typically form a black hole, because you have more mass than the model allows you to build a solitonic kind of solutions. I mean, there is no extra repulsion that helps in this case. You only have the wave equation of the scalar field. So you need to place them far apart. They will undergo this dynamical process where they collide and they expel some part of the scalar field, and then after this is done, then they will relax to start charge swapping. And this is what we see here, with one very nice thing, that is that these configurations are very long-lived. So we have not been able to see any of these formed configurations to later collapse. Not collapse, but migrate to an oscillaton solution. They always stay oscillating like this. This is just the charge in the upper hemisphere of the solution. This is five points here, and these 5 points are plotted here. This is the charge, the nether charge density of these configurations. We see them switch in time. This is the same plot as the previous one, the inset that I showed in the previous plot. And what I want to show you here is that there are mainly two frequencies that you can see with your eyes. I mean, you don't need to do any treatment to see these two oscillations. One is, of course, the charge swapping oscillation, which is in a Fourier decomposition. It is just this frequency here. And you also have these small wiggles, which are here. This is the frequency of this wiggle. And these two peaks, this is a sum of these two peaks. This is this one, and this peak is this one here. These are very clearly defined frequencies. And these frequencies are related to the scalar field frequencies. In particular, the difference between the frequency of the real and the imaginary part. So the reason this solution exists is because the real and the imaginary part of the scalar field are oscillating with slightly different frequencies. If you take the difference between these two frequencies, I don't know if you can, you can see there are two peaks here. And one peak is slightly to the right to the other one. If you take the difference of these two, you obtain the charge swapping frequency, which is the one here. If you take the sum of the two frequencies, then you obtain this peak over here. Okay, so that is regarding the dipolar configurations, but it can also be possible to form, as I was saying, multipolar configurations. We try to build the quadrupolar and the octupolar configurations, but with these values of the frequencies, it's not possible to do because they are very compact. And since you are superposing 4 or 8 boson stars, then they end up in a black hole. So we tried these two configurations, which are less compact. These are very close to the Newtonian limit. For example, you can see the compactness here. It is very, very small. And it is possible to form, for example, here I show a comparison between the dipolar case with D equal to 36 versus the quadrupolar with D equal to 36 again. And show the minimum of the lapse function, just to say that while the quadrupole survives, while the dipole survives, the quadrupole collapses. But when you take them further apart, then the quadrupole will survive and actually form a charge swapping configuration, which is shown here. So again, I'm showing here an inset with 3 configurations, and they swap in this way. Okay, and they are just switched like 45 degrees to make the simulations 2 times faster than the dipole case. Actually, it is funny because the quadrupolar configurations are double. They can evolve twice as fast as the dipolar configurations. I mean, in the numerical implementation. It is just a curiosity. But the behavior is the same. They are very long-lived configurations. So remember, this is T divided by T0 over here. And so these configurations live for tens of thousands of in time units of mu, of the mass of the boson of the theory. Finally, I will discuss about the third potential, which is the logarithmic potential. It is this potential over here, and these have certain motivations related to quantum theory and also effective field theory. It is also very interesting in the context of cuboids because they are exact solutions, very easy exact solutions in any dimension you want. And they call this soft potential because of some reasons I will show in the next slide. So here we build the boson star solutions in this theory, and they look like this. This is the exact solution, the exact Minkowski solution, and they go out of this sequence of solutions earlier as the gravitational constant takes place. This is just the effective gravitational constant, and it is increasing in value. And we see something interesting. When we evolve these isolated boson stars and make some perturbations on them, they are stable. All of the configurations that are to the left of the maximum of the configurations, they are stable, just as mini boson stars and Q stars and so on. But the binding energy of these configurations is of the opposite sign. This is strange, a little bit strange. I mean, the binding energy of this stable configuration is negative. No, it's positive, which means that they are expected to fragmentate and to be unstable, but they are stable according to numerical evolutions. And one difference with the other potentials is that when you use this kind of configurations to form charge swapping configurations, you see that there is no relaxation process. This means that if you set the configuration like this, it stays like this since the beginning, if you choose the very sufficiently small. And the left plot is just to show that the period of oscillation of charge swapping is the same since t equal to 0. Finally, I will talk about an application of this configuration. In particular, we said that this configuration can be formed in the free field case when they are very dilute. So the very dilute solutions are actually also used to model dark matter halos in the scalar field dark matter model. And I also said that the energy distribution of these configurations is not precisely spherical. It is slightly deformed, and it is slightly, let's say, a small dipolar component. Okay, it is not very strong, but it is a small dipolar component. And this actually reminds to some paper by Luis Ureña, Antonio Matos, and some other professors in Mexico, which they show that the combination of the spherical boson star, so if you combine the the spherical boson star plus a dipolar boson star, and you obtain, and you include some small portion of the dipolar contribution, and then form a dark matter halo, then you're able to solve the problem of the overabundance of, no, sorry, of the anisotropic distribution of satellite galaxies around the Milky Way. So we thought about this and applied one of these configurations of the less compact configurations to test the motion of particles around the gravitational potential formed. To do this, we just, since we are in very dilute configurations, we are able to apply Newtonian theory. So the Einstein-Klein-Gordon equations are just the Schrödinger-Poisson system, which has some nice properties. For example, if you find one single soliton solution to these equations, then you're able to make some rescaling to obtain another solution. You don't need to solve again the equations using your computer. I think I am showing here, yeah, the new scaling that it appears. So you not only have the rescaling on the mass of the boson star on the boson that we were using in the relativistic case, but you also have this rescaling, which is lambda, which allows you to modify in some way the compactness of the solution. And with these two parameters, we are able, for example, to reproduce the rotation curves of the Milky Way, for example, and use these values of mu and lambda to then obtain a solution and see how particles move on top of this gravitational potential. This is the paper that I was talking about, where they use this combination of the monopole plus a dipole configuration. And let me say a few words about what this problem is about. So if they look at the classical satellites of the Milky Way, or also some satellites in Andromeda or in M31, then it's possible to see that the angular momentum, the orbital angular momentum of these configurations are aligned in a particular way. They are not aligned isotropically. And in particular, in the Milky Way, they are aligned towards the plane of the galaxy. Okay, so they are not rotating with the, like with the matter, but they are like on the rotating in this direction here. So they are located around this line. Also, in a previous seminar, they told me that it is also not noticeable that they are located around this, but I don't know if this is a problem. I mean, they are located in a azimuthal particular direction, but I don't know any discussion about this particularity. I don't know. This is, I suppose this is not a problem according to astronomers. I don't know. Right. This is the gravitational potential that forms a charge swapping configuration. So even the configuration is dynamical, it is almost stationary. So what we did is extract one of this configuration at some snapshot of time, and we obtained this kind of configuration that you can see it is slightly deformed. And here it is a particle moving on top of this potential, and you can see that it is not along a plane, but the small anisotropy is able to deform to make them orbit in this particular way here. So as I was saying, we choose mu and lambda, the two free parameters to mimic the rotational curves of the Milky Way. And after that, what we did with this parameter set is put 10,000 particles in, and what we did is place them in a sphere with random positions with maximum radius, the size of the halo of the Milky Way, or the size of the satellites that are more far apart from Milky Way, and then put a random velocity that it is between 0 and 0.25 the escape velocity of some particle that it is on the edge of this configuration. And with this information, we can define a time scale, which is just the time it takes for one of these particles in the edge to make a turnaround in this potential. with this information, what we did is to evolve until 12 times the time scale. And then you can see that in the position space, these configurations are outside of spherical symmetry, which is okay. It is nice. But the really important thing is that the angular momentum of these particles, it coherently accumulates in the equatorial plane. So this is just like the Milky Way, and this is the reason this configuration can be used to explain the anisotropy in the Milky Way. In the case, the halo is made up of a charge swapping halo, and yeah, this kind of distribution of the particles we have tested with many values of the escape velocity and with a lot of charge swapping configurations, and the same happens. After some time, it accumulates like this, and it stays like this for a long time. This is just a comparison with the classical satellites of the Milky Way. And after all of this, we made a simple test, which is just checking that the disk of the galaxy, under this gravitational potential of a charge swapping configuration, it stays stable. It doesn't get destroyed by the effect of the anisotropic gravitational potential of the halo. Just following the paper by Donatiu and Luis Ureña and so on. The details about these charge swapping configurations and also the cosmological application can be found in this archive. And that's all, thanks.
Thank you very much. Do we have questions for Victor? Okay. Are there questions online, maybe?
Carlos.
Okay. Well, go ahead, Carlos.
Okay, so hello, can you hear me?
Yes, we can.
Okay, thank you very much. Thank you for the seminar. Well, I had several questions, but let me start with just the following. I'm not sure I understood completely, but it seems to me that you start with something that the total Noether charge is 0. Is that correct?
Yes.
So the Noether charge upon quantization is interpreted as the number of particles. Do you agree?
Yes.
Okay, so how do you interpret that? You have a configuration that has 0 number of particles. Are you kind of having a superposition of particles and antiparticles, or what are you doing?
Yeah, I suppose that the quantum interpretation is out. We didn't discuss the interpretation of these kind of configurations. But at the classical level, I suppose that it makes sense because they are oscillating with a different frequency, classical frequency. So,
well, but if I just look at, say, mini boson stars, and if I calculate the Noether charge, I get something positive, unless I put, well, at least with the right sign of the frequency. So, but here you have a sort of, well, we have negative Noether charges as well. And this is fundamental for your swapping. So I was trying to understand what's going on.
yeah, it is like a collision of a boson and anti-boson star.
Right. So that's what I thought. So you have particles and antiparticles in a way. And
yes.
Yeah. And so your final configuration, you showed us in one of your time evolutions, it tends to an oscillaton configuration. Is that correct?
Yes.
Which we know exist and are long-lived, and typically one constructs them out of real scalar fields.
Yes, these configurations at the end should decay.
Right, but they are long-lived.
Yes,
Okay.
all of
And-
them, all of them are expected to decay at the end. Even this very long-lived, they are expected to decay at the end because there is no nether charge.
Right, exactly. Oscillatons are composed of a real field, and therefore there is no nether charge. They in spherical symmetry, it's well known they can be very long-lived, but away from spherical symmetry, at least as solutions constructed not obtained by numerical evolutions, but constructed as a sort of stationary problem, which is not stationary anyway, but they've been shown to be long-lived in spherical symmetry. Yeah. And so what's fundamental then for having these charge swapping? I mean, at the end of the day, you're kind of starting with a superposition of two stars. It's a head-on collision in a sense, and people have done this for many years in many contexts. But here you're emphasizing this aspect that there's a charge swapping.
Yes.
And is it because there's particles and antiparticles? Is that the key thing then?
I didn't understand your last question.
So I'm wondering what's fundamental for the charge swapping, because
what you said, which is that you have to consider oppositely charged boson stars. There is a paper where Valenzuela studied the head-on collision, the first paper where they studied the collision of boson stars, and they explored this case where you have a boson versus an anti-boson.
Yeah, I'm aware. But in that paper, one of the things they notice also is that there is a dependence on the phase. So depending on the phase difference between the two, you can have that interaction is different. And at some point you were saying that there, if I understood correctly, that is, that there was no visible effect if you add an extra phase to one of the components.
In the polynomic potential case, in this free field case, the phase is more important. It can lead to a repulsion, a very strong repulsion that lead to some like harmonic oscillator kind of behavior of the, the solutions never merge and they start oscillating if you take a particular value of the phase difference.
Yeah, but in the Valenzuela paper, that's exactly what they see with the solitonic potential, yeah. So when they have a phase difference such that at the end of the day, you have that the scalar field has different signs, then they see a very strong repulsion. And in fact, that's the case in which you can construct equilibrium solutions. So as you are aware, there are dipolar equilibrium solutions in which you precisely have that the north and the south hemisphere have a different sign for the scalar field, which you can understand as a phase difference of pi. And so, well, I was a bit puzzled when you said, as again, if I understood correctly, that there was no visible dependence on the phase difference, because I think that's one of the points that in their paper was important.
Yes. In the case of the free field case, the phase difference is even more important than the value in front of the omega in the ansatz of the scalar field.
Mm-hmm. Okay. One other question, if I may, about this last application, which is interesting. So you start with the assumption that it's established there's an isotropic distribution of satellite galaxies. I've been actually discussing that a little bit with Jaramillo and Merced and other people. And well, is this really that well established and consensual? I would like to ask you, what's your opinion about that?
Last year, or maybe this year, they published a paper where they say that this is actually not a problem. They can take into account the movement of, I think it is Leo 1 and Leo 2, something like this, and they are able to to say that within the context of cold dark matter, it is possible to understand the anisotropic of this particular galaxy. But since this is also observed in some other galaxies, I think there is something strange. And if we believe the fuzzy dark matter scenario, I would expect that not only the spherical configurations appear in nature, but also some multipolar things like this in particular.
Sure, no, that, as long as they come from generic initial conditions, which is something still to be discussed. But my question was more into the kind of the established observations about this anisotropic distribution of the satellite galaxies. And for the analysis that you've done here, you've used the dipolar distribution. Was that the one?
Yes.
Uh-huh. So, and then at the end, you are analyzing the distribution of the angular momentum of the satellite galaxies. Is that correct?
Yes.
Yeah. Okay. So why then you get this sort of bias that, according to these observations, is there, that this angular momentum of the satellite galaxies is sort of not aligned with the angular momentum of the mother galaxy, but rather at 90 degrees. So why should a sort of a dipole induce that?
Yeah, so one assumption to get this conclusion is that the dipole is oriented with the galaxy, with the disk of the galaxy. Yeah, but it is, okay, this is the explanation. I mean, if the halo is oriented in this way, then the angular momentum of the particles will accumulate in this particular angle, which is the equatorial plane of the galaxy.
Right. Yeah, that's what's not kind of clear to me, because your dipole doesn't carry angular momentum, does it?
No.
So the only angular momentum is from the mother galaxy. So of course there's an isotropic energy distribution. But now you are saying this provokes an effect on the angular momentum of the satellite galaxies.
Yes.
And that's what's puzzling me. Why should, this extra component create this sort of deformation, let's call it, in the angular momentum distribution of the satellite galaxies? It's a bit intriguing to me.
Yeah, certainly. It is not. I think it can be argued with some kind of physical intuition of the movement of things around Newtonian gravitational potential, but this is just the way the particles move in these kind of potentials.
Mm-hmm.
For example, if you take seriously a dipole without a strong spherical component, then the particles do not accumulate in this particular way. They accumulate with less. They accumulate less in the equatorial plane if you have only the dipole. So it is a matter of taking a very small component of the dipole, which allows you to modify the angular momentum of the particles in this way. But you don't need the angular momentum of let's say, of the central object of the halo to obtain a modification of the angular momentum of the particles. You just need to make them move in a particular way.
Right, that's what you're saying. But wouldn't that be chaotic then, the motion? Because you have this multi-center gravitational center. Typically, you get a chaotic motion. And therefore, to get a bias for the angular momentum in a particular direction seems a bit contrived. But it might be there. Of course, there are some very particular examples, like the Euler three-body problem, or something in which you have integrability and there's some structure. But in general, it's chaotic. And yeah.
Okay. So are you talking about the gravitational potential that these particles create, or? Exactly.
So what I'm saying is that your mother galaxy, together with your kind of dipolar charge swapping dipole, is creating a multi-center gravitational center. And so if you analyze test particles moving around, typically this can lead to chaoticity. And nonetheless, you're telling us, I see a bias in the distribution of the angular momentum of the satellite galaxies. And then you justify, well, if I look to individual test particles, I can see there's a sort of preference for some sort of movements that explain this bias that I'm trying to explain in the angular momentum of the satellite galaxies. Yeah, and so that's intriguing to me. That's what I'm trying to, but perhaps yeah, it's something difficult to explain or to see the kind of simple principle that's leading to this. But of course, I'm asking to see if you have any further comment. Yeah.
No, I don't have any further comment, but let me just say that the gravitational potential is not multi-centered. It is centered at the origin. Maybe there is no chaotic.
But you have a dipole, right?
There is a dipole contribution. Yeah.
Yeah. So you can mimic the dipole contribution precisely by a multi-center. So it's in that sense, you see.
Okay.
Yeah. Yeah. Just the fact that the center of mass remains at the origin doesn't mean you don't have the effect of a multi-center mass distribution. Yeah. But anyway, so it's very interesting, and I thought that this is related to some ideas that we've been discussing. So anyway, I think we will have perhaps, I hope, time to an opportunity to discuss more. But let me thank you again for your answers. Thank you.
Are there any other questions? Maybe online, other people? Looks like it's not. So maybe then let's stop it here and thank Victor again